Unit 3 Chemistry, Chapter 8, Part 3, looking at changing equilibrium. So the person who investigated how we can change equilibrium was called Le Chatelier, or his surname was Le Chatelier. So it's his principle, Le Chatelier's principle. He noticed that if you take an equilibrium system and you subject it to a change, that system is going to adjust itself to oppose the effect of that change. So if you heat up an equilibrium system, it's going to do the best it can to cool down again. If you add more reactant, it's going to do the best it can to reduce the concentration of that reactant. Right? Now this is useful, very useful for industrial chemists, because it means that they can manipulate reactions to increase the yield. Yield, remember, is what proportion of the reactants become the products. So we can increase what proportion they are by making changes to the system that's going to force it to push that equilibrium to the right. Okay? So, the few ways we can do it. We can add an extra product or a reactant. So, if we have this equilibrium system and we add more nitrogen, that's increased the concentration of the reactant. The system, remember, wants to partially oppose everything that we do. Okay? So it's going to try and reduce the concentration of the nitrogen. Okay? By doing that, the only thing it can do is make more ammonia. So it's going to push that to the right, therefore increasing the yield. It's going to reach a new equilibrium with different concentrations, but actually, because we've got more of this and more of this, when it gets to that new equilibrium, the proportion of reactants over products, as defined by our K value, remains the same. So our K value doesn't change. Okay? You might see this sort of graph for that. Okay? You're seeing a sharp shoot up in the concentration of the nitrogen, and then it's partially opposing. And this is what we mean by partially opposing, because it doesn't get back down to where it was before. Okay? Because that goes down, hydrogen is on the same side, it's still also a reactant, so that goes down as well. Notice that the nitrogen goes down by much less than the hydrogen. That's because it's a 1 to 3 ratio. And that 1 to 3 ratio is represented in the size of these curves. Okay? The ammonia, being on the other side, is going to go up. Okay? And it was actually 1 to 3 to 2. So it goes up by twice as much as the nitrogen. Okay? If you see a sharp change in just one of them, one thing on your graph, then that means that you've added or removed, depending on which way it goes, one thing. The other thing we can do to alter the position of equilibrium is we can change the temperature. Okay? If you're thinking about an exothermic reaction, you could say that reactants become your products plus energy. Don't do that, but you could. Okay? So if we're increasing the temperature, the system's going to compensate by moving to the side which has got less energy on it. Basically, it's going to go in what we can think of as the endothermic direction. So if the forward reaction is exothermic, the backwards is endothermic. So that's therefore going to take in energy, okay, and therefore reduce the temperature of your system. Opposite is true, of course, of an endothermic reaction. Now this does change K, because we didn't make any initial adjustment to the concentration of anything. Yeah, so any change that's happening is actually changing that concentration fraction, the amount of products over reactants, so your K value will change. Changing temperature is the only thing that changes K. Okay, only thing. So we'd see something like this, and apologies for the blurriness, but you can still see the position of the lines. Okay? We're not seeing a sharp change, we're not seeing a vertical line up or down, we're just seeing a gentle curve that goes in one direction for our reactants and the other direction for the products. And we're also seeing, here we'd have a 2 to 1 ratio, this one would be the 1, this would be the 2, so we're still seeing that ratio represented. We can also change pressure. Now this is only helpful if we've got a gaseous equilibrium. Okay? But if we have a gaseous equilibrium, remember pressure is achieved by the number of particles that are banging on the sides of our containers. Okay? If you increase the pressure by decreasing the volume. Okay? Doesn't work if you add an inert gas, but if you increase the pressure by decreasing the volume, then your system's going to go, oh, it's too much pressure in here, and it's going to decrease the pressure. How do we decrease the pressure? By decreasing the number of gas particles. Okay, so we look at the total number of gas particles. On the left here, we've got 3, 2 plus 1. On the right, we've got 2. So if we increase the pressure on this equilibrium system, it would go to the right because that's got fewer gas particles. If there were other things in this equilibrium that were not gases, they would be irrelevant when we're looking at this. Okay. So here we might see that if we increase the pressure, we are doing that by decreasing the volume, so the concentration of everything goes up. Okay. And if you see a straight line up for everything, that is highly indicative that what you've done is increase the pressure by decreasing the volume. Then we get that partial opposition. So your O2 and your SO2 go down, not to where they started, but they go down, and your SO3 goes up. Okay, and by doing that, we are reducing the pressure because we are making fewer gas particles. For aqueous solutions, what we can do is dilute it. Okay, same basic idea as pressure here. Okay, we look at our aqueous things. Okay. And what the system cares about is how much dissolved stuff there is. Yeah? So if on this side I've got 2 separate dissolved ions, and on the right I've only got 1, if I then dilute it, then it's going to want to make more dissolved ions. So it's going to go backwards in this case, or to the left. Okay? Talking about it either way is fine. Okay? Until we make more of the reactants, and that therefore will reach a new equilibrium. Okay. As always, it's only a partial offset. So here we see everything going down. Now, when we see a straight line down, that could be indicative of dilution. It could be indicative of us decreasing the pressure by increasing the volume. So you just check whether you've got aqueous things or gases. Okay. In this case, we've got aqueous substances. In order to bring those concentrations of dissolved stuff back up, we're going to have a forward reaction. So these ones are going to go up, and this one will go down. And look here, we've got a 1 to 1 to 1 ratio, so they all change by roughly the same amount. Okay? You do need to be careful of that when you're drawing your graphs. The other thing to be really careful of, and use a ruler for, is making sure that these lines actually end up straight. Okay? Catalysts. Now, catalysts speed up the rate of a reaction, but they speed up the rate of the forward and the backward reactions the same. So they don't change the position of equilibrium. What they will do is make you get to equilibrium faster, and if we were looking at a rate of reaction graph, then we would see that that rate of reaction when they're both at equilibrium is higher. Okay? But the position of equilibrium stays the same. One final point on equilibrium. It's important to be aware that not all reactions reach equilibrium. Most do, but not all. Some of them will only reach equilibrium if they're in a sealed container. So if one of our products is a gas and we have an open beaker and that gas escapes, well, that means that we're then having a very low concentration of that product, so we're going to keep on, by Le Chatelier's principle, trying to make more and more and more of it until we can get to an equilibrium. Okay? And we'll keep doing that until all the reactants get used up. There are others like, for instance, the dissociation of hydrochloric acid. Yeah, very strong acid. That's going to go so far to the right that we only get a tiny amount of the reactants left. And so, whilst it probably is technically at equilibrium, we can't detect any HCl in there. We can detect hydronium ions and chloride ions, but no HCl together. So we'd consider that as having gone to completion.